Okay, the meaning of this integral. First place, it becomes a little clearer if you put parentheses here. It means evaluate this, treating y as your variable and treating x as a constant. Now you're used to treating one or the other as a variable, the other as a constant, so that shouldn't be any surprise to you. So this gives you the integral of, I'll use parentheses, of the quantity integrated with respect to y, it's going to be x y cubed over 3 plus 3/4 y to the 4th over x. Okay. And, this is a complex fraction, so you say, okay, that's the integral then of x y cubed over 3 plus 3y to the 4th over 4x dx. And then you can integrate this with respect to x, which is also very easy. And I'll just do that for you. This equals x squared y cubed over 6 plus 3y to the 4th over 4, natural log of the absolute value of x, plus a constant. Now, there's one thing I left out because I didn't want to confuse the issue. You notice I added a constant at the end here. Well, really, I should have added a constant when I integrated here. So really, this should have been plus C1. And then I would modify here by adding the C1. So instead of adding a constant on here, I'd be adding a C1x plus a C2. That makes sense? The constant that I add on when I integrated with respect to y then has to be integrated with respect to x. Yeah, this is easy. As long as you don't have things like arctangents of exponentials and stuff. Okay? And you do the same thing here. If it's a definite integral, then you don't need the constants because they just subtract off. You evaluate it at this limit and this limit, you have the same constant at both limits. So when you subtract the two, they go away. You don't have to worry about integration constants. Okay. I want to start with the idea of a definite integral over a rectangular region, which is what we're kind of looking at there. Okay, so we got a rectangular region. And we got a function, f of x, y. I don't know where the axes are. They're out here somewhere. There's a rectangular region somewhere in the xy plane. It's bounded by x equals a, x equals b, y equals c, y equals d. So it's not only rectangular, but it's rectangular with the sides parallel to the axis. Now, if everybody's had linear algebra, you know how to rotate axes and stuff. So if you do have a rectangle that's at a weird angle, you can just rotate your axes. Get them parallel. And you know, use your sines and cosines and all that stuff. Okay. You might not remember how to do that. It's easy. Yeah, semi-easy. Okay. All right. Now, since I'm in the habit of not knowing whether I'm recording or not, okay, now we have some function. F of x, y, function of two variables defined on a rectangular region. And you can't read all that, but it was. You can, but anybody watching the video couldn't. Okay. I'm going to divide my region up into squares. Presumably equal squares, although I didn't do a very good job of drawing equal squares. Okay. I choose a sample point in each square. Anywhere random in the square. It's probably best to be somewhat random if you're trying to approximate the integral. Like if you go to the center of the square every time, there's probably some systematic error that you're making. Whereas if you do it randomly, you're making random errors. But there's an art to figuring out the best. You probably don't want points to be too close together either, so maybe totally random isn't a good thing. Maybe there's some statistical distribution that would give you the best possible result, or would give you a statistically superior result, meaning one that's more likely than any other to be close. Okay. And you don't need to understand all that. Just a little digression. Okay. So we have these sample points. The integral is going to represent the area under the surface. You see, we've visualized our surface over there. Okay. We've visualized what the curve looks like here, what the curve looks like along here, what the curve looks like along here. If we slice the thing and set it up and look at it, okay? Got all that in our head. It's a good start. I never had the sense to do that. So, you know, eventually I'll figure things out. Okay. But I think that's going to be beneficial too. If I know f of x, y, then how, and if I know what A and B and C and D are, am I going to be able to get an approximation of the area or the volume underneath the surface? What would I do to get the approximate volume of this square here? Let's talk about it for now. Okay, now we've spent a good chunk of our time just grasping what we mean by sample points and volumes and areas and making suggestions. If you have that firmly in your graph, then you begin to understand how you can set up intervals like this. Okay. Matter of fact, if this was your function f of x, y would go from C to D. X would go from A to B. There's the interval. It would give you the exact volume of that function, if that's your f of x, y function, on this rectangle. Now you approximate that by by breaking the thing up into squares. And then you think, okay, we can keep refining it. What if I built a structure out of dominoes instead of out of dice rather than dominoes? Okay. Smaller and smaller squares. If I divide this up into more and more small rectangles, my result is going to be closer and closer to the actual value. Right? Okay. Okay, well, if this is the integral, and of course now we could just replace all our x's by, all our y's by c's and d's and all that stuff. Just subtract what we get at the upper limit, at the lower limit from what we get at the upper limit, right? In other words, the familiar thing you do when you do definite interval. Let's say we did that, and let's say we had numbers here. So we get a number at the end. Down here, instead of an arbitrary function, we would get some number. 43. Okay. Okay. How would we find the average value? Let's go back to our stack here. What do you think the average value of C is for this whole thing? Nominal thicknesses are all fairly small thickness, right? I think this stack has down.
Two.
Sorry?
About 2.5 dominoes.
About 2.5 dominoes. Yeah. It's there's some average value there. If this was whatever the surface is, and you melt it down into the same rectangular footprint, then we would end up. That should have been about.
Yeah.
You do the integration, you need about the area. And be sure you know you divide the interval by the interval for function done to get average value. The four goals in your text. Fourth one being figure out the interval. That's the one place where it's in. that you need to look at. Okay? And also, think in terms of average value lies in the estimate. If the average value is 3, then how many dominoes do I have in the stack? Dominoes, by 3 dominoes, that's 12 square dominoes, right? The average value is 3, that means I have 12 times 3, 36 dominoes in it. Okay. Now, the actual surface is rounded, probably comes up higher than that sample point, just because it's running past here. Rather than a peak around here somewhere. Yeah, you think on this. Okay. Well, that's the first thing I want you to understand. You're going to see it in your text, which I do want you to read so you understand the notation. I'd rather give you a concept at this point than the notation. The mechanics, again, are simple. So let's just give me 1 second. You could easily figure out the area of this thing, right? Width is 4, the average altitude is 3, so the area is 16. Okay. If I wanted to do an integral over this region rather than over a rectangle, I'd have to describe the region by inequalities. I can say, for example, zero is less than or equal to x less than or equal to 4, right? Okay. Now, if I say 0 less than or equal to y less than or equal to 5, that implies a 4 by 5 rectangle. Is that clear? Now, the idea is for every x between 0 and 4, and implicitly, the footprint of this rectangle is the same as the footprint of this trapezoid, okay? For any given x, what are the limits on y? This says for every x between 0 and 4, y goes from 0 to 5. Does that make sense? So pick this x, y goes all the way up to 5. Pick this x, y goes all the way up to 5. Okay? And I could equally well describe it as 0 less than or equal to y less than or equal to 5, 0 less than or equal to x less than or equal to 4, which would mean for any y, x goes from 0 to 4. For y up here, x goes from 0 to 4, right? So I could describe that integral in either order. You're going to see that in the first section. And it's easy. I can't do that here. If I use fixed numbers in my inequality, that means I've got a rectangle. Over here, you got to say, okay, well, 0 less than or equal to x less than or equal to 4. For every x between 0 and 4, I've got a straight line segment along that line enclosed within the region. Okay. no matter where my x is, I can do this. Okay, if I tell you where x is, can you tell me what the lowest y value is 0? Can you tell me what the highest y value is? Well, I'm going to tell you. Y-intercept here is 3, right? The slope, let's say you got a run of 4 and a right, slope's 1/2. So on this line, usually write that 1/2 x plus 3. X is, or y is going from the line x equals 0 up to the, sorry, from the line y equals 0 up to the line y equals 3 plus 1/2 x, right? So we could say 0 is less than or equal to y is less than or equal to, I'll write it 1/2 x plus 3. That's where we want to see it. Okay? You get the idea? You're going to have to be able to describe regions by inequalities. And very soon, three-dimensional regions. Okay? I think this week just two-dimensional. Next week, we'll talk about how to do a polar coordinate. I mean, next class. Okay? Let's say then that f of xy is an easy function, x squared y cubed. Okay? Integral over the region of f of xy with respect to area. You construct that, R is the region. R is the trapezoid, it's in the xy plane. Okay? We're integrating not with respect to x or with respect to y, but with respect to area. Okay? To integrate with respect to area, we need to do a double integral. Okay? Now, there's only a single integral sign, but it's a single integral over a region, and it's a two-dimensional region. If it was a three-dimensional region, we're going to use a if it's a 3,000 degree, 3,000 dimensional region in data space, then we're going to have to do a nested set of 3,000 intervals. Okay? Better have good software. Okay. So we have this double integral of f of xy, which is just x squared y cubed. And the area is dy by dx. It's like a delta y by a delta x. That's an area. Okay? And then to do the integral, x gets integrated from 0 to 4. Y gets integrated from 0 to 1/2 x plus 3. Got that little bunched up there. I don't know if you can read that, but it's these limits from 0 to 1/2 x plus 3. You can do that integral. And you can divide by this area, which is 16, to get the average value. So let's just do the integral real quick. I'll do it for you. I could ask you to do it if we had a little time. I'm sure that you would get it. Let's write it out big enough that you can read it. let's see how this works out. Kind of need to know how it works out. First thing I'm going to do is put parentheses around the thing that we're integrating first, which is this with respect to y. This is the integral from 0 to 4 of and a derivative of x cubed, x squared, y cubed with respect to y is x squared, y to the fourth over 4, evaluated between 0 and 1/2 x minus 3 with respect to x. Okay? Make sense? I know you can see the antiderivative, and we're just evaluating these. Well, if I do that, that's the integral from 0 to 4 of, and we need to be careful. We integrated with respect to y, so I'd like to write y equals 0 here and y equals 1/2 x minus 3 here, which prevents from accidentally looking at x and substituting these things for x, which would be a disaster. Okay. So that means we have x squared times 1/2 x minus 3 to the fourth power divided by 4 dx. I think it's using binomial expansion. I'm going to factor out my 1/4, so that's one less thing to get confused about. It's going to be x squared times x to the fourth over 16 minus 6 times 3, 18 x cubed over I'm losing. It's probably wrong. And then x squared times 3 squared, which is 9x squared. 1/2 has to be squared, 9/4 x squared. That's got to be multiplied by 6. And plus 81 with respect to x. There's probably at least one mistake, maybe 12, in what I just did in my feeble brain. We've got x to the 6th over 16 minus x to the 5th over 4 minus losing track of where I am. Yeah, it's got to be x to the 4th, and it's 54/4, which is 27 halves. X to the 4th. And I sure have lost something. It's definitely wrong because I don't have an x term here between the x squared and the 81. So yeah. Okay. Anyhow, this equals something. And it's not difficult to figure out. You probably use your calculator, it's okay. Although it's good for you if you can do it with the numbers. You want to write out the binomial expansion. A plus B. The fourth is a to the fourth plus 4ab cubed, or a cubed b, plus 6a squared b squared plus 4ab cubed plus b to the fourth. I left out this one. And I probably made mistakes in the other ones. Okay. You know Pascal's triangle? Might show you that. Let's see. Look it up. It's really simple. Pascal's triangle. Uh, it's a high school level thing. But you might have a statistics for engineering course in your future. It wouldn't hurt you to get a little bit of a conceptual background, how this is related to statistics. In your spare time, and I know you got a lot of spare time, make a note sometime when you do have a spare time. Start making a list of things that you really ought to probably think about. In your engineering on this course, things you don't have time to think about, but know you ought to. Okay? Just advice. So anyhow, you get a number here. And the number you get here is the volume of this surface, which is kind of, well, I'm going to try to gesture it. Okay. You divide that by the area and you get the average value of that function, which is often a very, very important. Okay. So we've got a question. You're going to integrate the one with the fixed limits last. In other words, I can now plug in 0 and 4 into this thing and I'm going to get a number. Okay. If I tried to have the limits 0 to 1/2 x plus 3 on the outside, I wouldn't get a number. And I'd be substituting for my x before I'm done using my x's. If that makes any sense. And it probably will the first time you try to do that. It's one of those things, if you do it wrong, you learn real quick. And it's usually an uneasy problem. So you don't waste a lot of time learning. But there's your warning. The fixed number is the one on the outside integral. Inside integral, the limit on that integral should match the variable in your outer integral. Okay?